In this video, we're going to continue looking at Lewis structures that don't follow the octet rule. In this case, Lewis structures for molecules where some of the atoms have more than an octet, more than you would predict. I think I'm done sneezing. I took a little break to make sure it was all cleared up there. All right, so let's look at a particular example. This molecule, SF6, sulfur hexafluoride. So this is actually a really interesting molecule. I think we talked about this one briefly when we were talking about naming compounds. But this is a molecule, it's a gas, but it's a gas that is very dense. And so if you breathe in sulfur hexafluoride, it does the opposite of helium. Helium makes you talk in a really high-pitched voice. Sulfur hexafluoride makes you talk in a really low-pitched voice. So it's a really, you should look it up on YouTube if you can find a video. It's really interesting to hear it. It is thankfully non-toxic, so you can do this. Anyway, let's think about the Lewis structure of this compound, though. So sulfur is the central atom here, but we have to fit 6 fluorines around it. So we're going to have a single bond to all the different fluorine atoms. There's 4, 5, 6. We'll add valence electrons to all, or lone pairs to all of the fluorines to make sure all of them have an octet. And we're done. We can count up, but this should give us the correct number of electrons. We'll just double check that. So sulfur has 6, like oxygen, and fluorine has 7. So that's 6 times 7. So we get a total of 48 electrons. 6 times 7 is 42, plus 6 is 48. And one way we can count this up is all of these are the same. So they all have 8. So each fluorine has an octet. So we can just multiply by 6 fluorines, so we get 6 times 8 is 48. So we have the correct number of valence electrons in the structure here. Okay, so all the fluorines are pretty straightforward. They all just have octets. They form one bond, which is pretty normal for halogens. Compounds that have one unpaired electron left to participate in bonding. But sulfur, on the other hand, has formed 6 bonds, and so it has 12 valence electrons. And so this pretty clearly violates what we know as the octet rule. But this is the correct structure for sulfur hexafluoride. Sulfur hexafluoride doesn't care that there's an octet rule. It forms a nice stable compound. You can buy it from a store. It's used in different places. So this is an example of something with more than an octet. Now, when are we likely to see these? Well, one thing is things with more than an octet generally occur with third row of the periodic table and below. So this is the point at which the electron orbitals are closer in energy, and you have additional orbitals like the D and F electrons that are available that can maybe be part of this bonding as well. But if we go to the periodic table, right, all of our elements that we spent a lot of time looking at are right, carbon, nitrogen, oxygen, fluorine. These do not generally violate the octet rule. There are exceptions to that. For everything we talk about in this chapter, there are exceptions of molecules that exist that break the rules. But 99% of the time, these are not going to break the octet rule. And so it's generally you're going to start seeing it with elements that are down in the third row or below. Once you get down here, so it's kind of like all bets are off in some sense. For example, neon never forms any compounds with anything else, so it's pretty unreactive, and helium too. But once you get to argon, it's still not very common. But krypton and xenon, it's difficult to do, but you can get them to form compounds. And same thing with some of these other elements. They will form compounds with what we call hypervalent. So that's sometimes the term that's used for this having more than an octet is. It's called hypervalent molecules. Right, so this is one example, sulfur hexafluoride. So sulfur being in that third row of the periodic table, this is an example of a compound that can do this. Let's look at some other ones. Again, they're going to involve these third row or below elements. So we'll look at another sulfur compound here and combine talking about a few different things that we've talked about. And this is actually a really common ion that we see a lot, sulfate, SO42-. So sulfur is the central atom here. Let's count up our electrons first. So we have 6 for sulfur, plus 6 for each of the oxygens, so 4 times 6, plus another 2 electrons for the charge. So we end up with 24, 30, 32, total electrons. Sulfur is going to go in the middle. We can write our single bond to everything else. Make sure we don't forget to write that this has a 2- charge. And then we can add our valence electrons here. All right, and how many electrons does that give us? Well, it gives us 8 times 8. This is 32 electrons. All right, so we have the correct number of electrons. Okay, so we might think, okay, we're done. This is good. Well, this is one of many possible resonance structures for this compound. And so let's look at the formal charges and see if this makes the most sense in terms of formal charges. So each of the oxygens, they're all going to be the same. So the formal charge on the oxygen, let me just use a color here. So we'll look at one of these oxygens, and it's going to be the same for all the oxygens. So the formal charge is equal to 6. That's our normal number of electrons for oxygen, minus our 6 electrons that are in lone pairs, plus our 2 electrons shared with the sulfur. So that gives us 6 minus 7, which is equal to -1. Okay, so all of these oxygens have a -1 formal charge. I'll write it like this. So I'll have a negative formal charge. What about the sulfur? All right, so now let's look at sulfur here. So it also has 6 normally. There are 0 lone pairs plus 8 electrons that are shared, which gives us a total of +2. Right, so sulfur has a 2+. And this does work out. If we add up all the formal charges, we get overall -2. Remember, this is an ion, so it should have overall -2. All right, but we have not minimized the formal charges in this structure. So there's a different way we could write. There's a different resonance structure that we could write here. And I won't write all of them. There are actually multiple. But we can pick 2 of these oxygens to share their electrons with the sulfur in the middle. So we can have an alternative resonance structure where we have double bonded oxygens and then single bonded oxygens as well. All right, so these oxygens are still going to have a negative formal charge. Those aren't going to change from what we calculated previously. But now both the sulfur and the other oxygens have now changed. We'll put it in yellow to indicate that they're different. These are all 0 now. You can go through, pause the video, and double check for yourself if you don't believe me, but all of these have 0 formal charge. So again, that matches our overall charge. We have a 2- charge here. But this alternative structure is minimizes formal charges and ends up being the most important structure. Even though what's different, the main difference is that sulfur right here, again, has 2, 4, 6, 8, 10, 12. It has 12 electrons around it instead of our usual octet. So this is an example of a molecule that's breaking the octet rule because it minimizes the formal charges. And you know, the version where it's all single bonds is still a valid resonance structure. But this version where the formal charges are minimized, and there are multiple resonance structures we could write here, right? So the double bonds could be in any of the positions, just as long as there's 2 double bonds and 1 single bond. But I'm not going to write down all of those different formal charges. All right, so one other trend you may have noticed, in addition to our central atom being something that's from the 3rd row and below, is it's often very electronegative atoms. Electronegative atoms that are bonding with them. So we saw with sulfur hexafluoride, it involved fluorine. With this compound, it involves oxygen. That's a pretty common trend with these compounds where they exceed the octet rule. All right, so there are lots of other examples we could look at. We'll look at some more. But this being a very common ion that we see a lot, it's one of the ones that you've memorized. It's a nice one to look at. We'll look at some additional ones in class and on your homework as well. So that's it for expanded octets, what we call an octet, something that has more than an octet. In our final video on these sort of exceptions to the Lewis structure rules that we've learned up to this point, we're going to look at things that have less than an octet.